Hello everybody, welcome back. Sorry for the little bit of delay on this lecture. It's been a crazy time with midterms and all that, but we are getting it out to you, and I think you're going to really enjoy this one because we're going to start to crack the analysis open. We're going to give you a chance to actually see a little bit of what the sciencey bit of data science actually looks like. We'll be talking about descriptive statistics and a bunch of different things along the ways of understanding what is in the data. So before we get into it, we have, as always, some course reminders. So because I'm recording this right now at 12:49 a.m. on Thursday morning, you will be seeing that reading number 3, the quiz is already live. So please go ahead and take a look at it. It's about the tidy data readings. So they're pretty much just elaborations on the stuff we already covered during data wrangling. Now, the bigger thing is that assignment number 1 is coming up. You've got a little over a week at this point. So by the time you turn in assignment 1, you should have a fairly firm idea of what you would like to do. Now, obviously, you're not going to have all the T's crossed and all the I's dotted or vice versa, okay? But you do have to have a solid proposal in there that we can evaluate for whether we think this is likely to come off or if it's a completely wrong direction. And of course, the more you can have done, the more we can give you guidance and the further along you will be on your way to the final project. So please, only one submission per group. And obviously all the other stuff is going to be completed as individuals except for the final project. Also a reminder, there's a big packet of information about assignment 1 and the final project on Canvas. So you can get examples of really good past projects. You have a guide about how to be in a group and have a good vibe in your project. And you have all the information that you need to know really what the actual assignments are and what they might look like. Okay. All right. Finally, it is just past midterm. I would love to hear from you. What is going down in this class from your standpoint? How have things been? What's been bad? What's been good? Please fill out the mid-course survey. You can find the link right there. Now, obviously everybody's quite concerned with the grades, and we're working really hard that within 1 week after the exam you'll have that all back, and that also is true the 1 week for the quizzes. So you should have reading quiz number 2 back to you very soon. All right. So today we're going to describe some data, and the objective is that you, at the end of this, should be able to identify data analysis that's asking a descriptive question. You should be able to understand what that kind of analysis looks like. And also, you should be able to describe some data, because we're describing stuff. Yeah, titles. So, let's just jump right in. So, this little quote that we somehow completely eliminated the name of the person on. I guess it's right there in the link from Simply Analytics. Data science is the process of formulating a quantitative question that can be answered with data, collecting and cleaning the data, analyzing the data, big underline there, communicating the answer to the question to a relevant audience. So, right, clearly, to do this, you need to not just look at the data, but describe it and explore it. Okay, so what do those things mean? Those are two kind of different ways to look at data. Here is a lovely diagram, and I'm going to get my face out of the way. Okay. So, what we're seeing here is a way to look at some sort of output and see exactly what kind of data analysis it was. Now, let's see here, get my highlighter tool out. So when you see something, obviously if it doesn't actually summarize the data in some fashion, if it's just the data in a printout, or if it's not data-driven at all, it is not a data analysis, right? But if whatever you're looking at, whatever kind of analysis you're looking at, if it describes the nature of the data in some sort of compact, summarized fashion, but it doesn't tell you what to think about the data, right? It's just dispassionate. It doesn't have an opinion. It doesn't cast a spin or tell you how you might interpret that. Then it's a descriptive data analysis. Okay, so then you're down here. But no, if you do add some interpretation, if there is some sort of, we think this means, or perhaps this suggests that we should further explore, right? Anything like that, then this is not a purely descriptive endeavor. Now we're doing something that is perhaps exploratory. And it's exploratory if we think that we don't have a great amount of confidence that this is going to be true when we go out and do this again, right? If all of this was about Twitter and Twitter sentiment, right? Then do we think that will still be true tomorrow? Or would it still be true if we grabbed users from Kazakhstan? Or would it still be true, So this is going to generalize to a whole new sample that comes from fundamentally the same process. If we're not sure, if we don't feel very strongly, then this is an exploratory analysis. Typically, what happens is that when we are first starting to look at a brand new topic, we don't really have a strong idea. We just kind of jump into the dumpster and we root around in the dumpster of data and we see what we can find. We look for big picture kind of stuff because we don't want to be fooled into thinking that randomness is the real thing going on there. Okay, we don't want to take random things that are in a data set and decide that they are big trends that will hold forever. So that's an exploratory kind of a data analysis. Now, if on the other hand, people have done this kind of analysis before, if there's a background, an idea of what we would expect, we've done these kinds of experiments where we send students to do this kind of task before. Now we just have a brand new group of students doing the task and we want to measure them and find out what's going on. Then we're over here into the branch of proper statistics. Okay? So over here, this is all the stuff that you generally find in a statistics class or an advanced statistics class or a modeling class or etc. So are you trying to figure out how changing the average of one measurement affects the other? If that's true, then we're down on the branch where we're trying to determine causes, okay? And if causes are statistically present, average, then this is some sort of statistical causal model. And if what we're looking for is a deterministic thing, like physics, okay? You swing the hammer and you hit the I don't know, what do you call those things at the fair where it's like the giant lever that moves a weight up the straight pole, and then at the top it rings a bell if you're really strong. I don't even know what those are called, but that physics, right? The swinging the hammer, hitting the lever, making the weight slide up the pole, that's deterministic. It's always going to happen the same. Once you determine the inputs, you know what the outputs are going to be. Whereas a statistical system has randomness, and you can't really know for a given set of inputs, you'll always get the same outputs. So these are models, though, fundamentally of cause and effect. Now, if you're not trying to find out how one thing changes another, then you're in the classic stats world. Inferential, where you're trying to, understand something about a particular group, or predictive, where you're trying to predict the future, right? All right. Inferential stats is what most people think of as stats, by the way. And you will learn more about this. But today, we're in descriptive. So really what we're just trying to do is understand what is happening in a given set of data. Okay? Nothing else. We're not going to try to apply theories or hypotheses like you would in inferential statistics. We're just going to see, what do the data look like? Because that is the first step, ladies and gentlemen. All right. Yep. There we go. So what is it like to do something like this? Well, maybe you are familiar with the good old-fashioned elephant being examined by a bunch of blind people. You've probably heard the folktale, how each single one has a completely different idea of what the elephant is because they've each got a different part. Oh my gosh, it's a snake. Wow, it's a tree trunk, right? Etc., etc. I don't remember the rest of the folktale, by the way. But yeah, you get the concept. That's what it's like to do data analysis. You see little pieces of the puzzle, but you don't see the whole puzzle, right? So this is very much you on each one of these stations with a different piece of the puzzle. And that massive data set you're grappling with, you need to try to piece together what it is, how it looks. Okay? So we can do that with some good old-fashioned sampling and statistics. Let's start with a good concrete example. You want to understand something about how and whether users are nice or mean on YouTube. Okay? So we have to formulate a question. Are the words that people use in their comments more frequently positive words or negative words? And I would add the caveat that you might be able to answer this for a certain kind of video or a certain place, but maybe there's subgroups in this data that we're going to find later that we're going to have different results with. All right? So this is the kind of analysis which is descriptive. We don't really have a hypothesis yet, although I've just floated one that there might be subgroups. But we're going to just pursue this as, let's just take a look at everything all at once. All right? So, to answer this, we would have to calculate some statistics about the sentiment of YouTube comments. So what are statistics? We deal with the classification and collection and analysis and interpretation of numerical facts or data and use of theories of probability that impose order and regularity on aggregates of more or less disparate elements. That sounds terrible. I know statistics pretty well, and I only recognize half of that, right? But really what it is it's just the art of measuring things when we have a sample and we want to use that sample to better understand a population, okay? But let's just go right to the jugular here. This is a quantity. A statistic is a quantity computed from a sample, like I was just saying. What is a sample? Okay, well, we have every person in the United States of America, right? And we would love to know something about their usage of YouTube, all right? We would like to know if their comments they leave are nice comments or mean comments. And, well, clearly we can't maybe get at every single person in the United States of America. If we were doing this YouTube thing, maybe we have that data available, right? But it's hard, too much data. If we're doing something else, not YouTube's, but like measuring blood glucose, there's no way we can measure the blood glucose of every single person in the United States of America. It's not going to be possible money-wise or time-wise. So, or getting people to do it wise. So what we have to do is we have to find ourselves a sample, a small group of people that are somehow representative of the population at large. If your sample is a bunch of randomly drawn people and you draw somebody in randomly according to their properties, okay, so that on average we have about as many of the dark colored people as there are in the population and as many of the green colored people as there are in the population, that those proportions are similar within a factor of random, right? Then we have a good sample. Then we can, assuming we have enough people in the sample, we can draw an inference. We can say whatever we calculate in here is likely to hold true in the population as a whole. So it's a round trip. We've got to get a good sample that represents the population, and then we are able to therefore use statistics we can calculate on the sample to infer properties about the whole population. Yay, stats! Hopefully many of you will truly enjoy stats, because this is one of those things that may seem a little scary, but once you get used to it, it's really brilliant. I can definitely recommend that if you get past your trouble point with statistics, you will certainly make yourself A, comfortable, and B, very, very useful, because I mean, obviously data analysis, statistics, if you're doing data science, but just in general, the person who's good at stats in a group of people becomes a popular person. All right. Let's take our example. Let's work it. Okay. So what is the population? All comments ever made on YouTube. I have no idea how big that number is. I went looking for it in a quick Google search. I could not find it. What I could find is this little quote that just in the second quarter of 2020, over 2 billion comments were removed from YouTube because of violation of community guidelines. That kind of implies the number of YouTube comments is insanely large. So, probably we could not computationally ask a question of the entire population of YouTube comments. Maybe you could with cloud computing, potentially, but certainly it seems like that number might be big even for that. No way you're doing that on your laptop. So let's get a random 1 million comments from sometime in the year 2020. That's going to be our sample. We're going to draw 1 million comments. Okay? So any statistic is a quantity computed on the sample, because the sample is what we have access to. Okay? And the sample is standing in for the population. All right? So we're going to calculate our positive and negative words on our YouTube 1 million comments. So again, sampling is important. You need to get a good sample, one which is representative of the population. If for some reason, because the world is like that, you know that your sample is biased. You know that it contains too many of the little green people and not enough of the dark gray people, or something like that. Then you need to figure out a way to either don't claim that your results are going to generalize. That's the easy way out. Just be like, hey. Okay. Or another way is that there are in advanced stats ways that if you understand the way your sampling is wrong, that you can correct for that. Advanced topic, not for this course. Okay? All right. Now, examples of bad sampling. What do you think is wrong with looking at asking questions of gun magazine subscribers about their attitudes towards owning guns? It is almost certainly not going to be representative of the general population. On gun ownership, the United States is severely divided. And basically, if you live in a rural area, you are highly likely to be rather pro-gun. And if you live in an urban area, you're rather likely to be anti-gun. So there's being very bimodal. And if you only sample on one mode of the bimodal, sorry, we haven't actually introduced the term bimodal yet, but we will. So there's gun owners and not gun owners, and they're very different. And they're going to have a very different statistic, and we're going to get to that. Okay? Now, it may be less clear. What is the problem about sampling Facebook users for TV shows? Right? Why would Facebook users not be representative of all Americans? I can wait here all day until one of you answers. Right, I'm not going to. Because the thing is that people who use Facebook might be very different than the larger population. Facebook tends to skew old compared to other social media, right? And also, it tends to skew more towards a higher end of the socioeconomic spectrum because Facebook is fundamentally a social media platform that was originally aimed at college-educated people, and it's kind of stuck there, right? Also, I mean, there's still a sense in which maybe social media is not something every single person in this world has. So, you have to think, right, and especially in the internet age, there's a real, there are data sets out there that are easy. They're easy because they're internet data. Things like the Twitter stream and the Facebook stuff, okay? Because they're internet data, they're available. Anybody can get them. And so you're tempted to ask questions with them. But if you don't stop and think, the limitations of using that easy data compared to going out and burning some shoe leather to get data that's more representative of the population, right? You may not get results that generalize. Okay. So also, you obviously wouldn't want to just sample a single YouTube channel or a single language potentially, right? You would want to understand all comments, and that could get very big very fast. So this is just what I said, right? If you've got a bad sample, if you're not getting an accurate data set that's going to tell you anything about the rest of the world, you've got nothing, basically. What you've got is a lot of wasted electrons and hours. All right? So it's always worth spending time at the beginning of a project to determine whether or not the data you have are garbage or useful for the question that you're after. Okay, let's say that you think your data set is a good sample. Now, how do we describe it? Well, there are a kind of a big 5 of descriptive analysis. Okay? Data size, what's not there, the shape, the central tendency of the data, and the variability of the data. All right? So we're going to go through each one. So this is a quote which fundamentally gets to why we even are using stats, right? I'm going to get a little kind of highfalutin here, but there's a rather famous author from the last century called Luis Borges. I'm not very good with the Castilian Spanish. And he wrote a very interesting short story where it was kind of a weird, bizarre thing where, somebody made the king a map which had every single detail of the entire kingdom. The problem is to have every single detail in the entire kingdom, the map had to be the same size as the kingdom itself. This made the map kind of useless because one could not fold it up and put it in your pocket and do anything with it. Now, okay, this kind of fantastical short story is often used in various kinds of academic circles to talk about the fact that models are all abstractions, right? Everything to help us human beings understand better has got to abstract away detail. We've got to throw out detail so that we can get to something we as humans can grasp and handle and stick in our pockets for later. Okay? And that's why we're even doing this undertaking. So, because let me tell you, if you had to look at raw data all the time to make all your decisions, you would cry, especially once it gets a little bit big. All right, so today's example, we're going to pull from the data you gave when you filled out the student survey at the beginning of the quarter. All right, so what does this data look like? Well, it's a spreadsheet or a comma-separated value sheet, right? It's tabular data. And there's different columns which have things like your hometown and your ethnicity, which has things like what was your high school GPA, and what kinds of technologies were you familiar with at the beginning of the course. All right, I want to point out a few interesting things. So this is your height in inches, 508. Ooh. Most people are in the 60s or 70s, so I'm guessing that person meant feet. This is so typical, right? Data wrangling class. Here is some unclean data. And boy, is this data unclean you lot gave me. You should see how many different ways there are to say male or female. All right? Or non-binary, right? I mean, at least that is a recognized category, but that's a misspelling there. Okay? And capitalization problems versus non-capitalized, etc. This is the data wrangling nightmare that we all know you are going to face during your careers. All right, well, we're here for statistics, not for data wrangling. So let's start off. Size. Well, you gave me 454 observations. 454 times somebody filled out this form. Now, I don't have quite that many students in class, so a few of you clearly did it more than once, but there we go. I think the number is just over 400 now in the class. All right, there's 30 columns, 30 variables that we measured. Okay, and why do we care about size? Well, we care about size for a variety of reasons. Some statistics are normalized by the size, like the average, the mean, right? And also, you need to get a sense in which you understand how many observations you have in your sample, and is that enough to adequately draw an inference about the population as a whole. All right. Missingness. Messy data. Messy data has missing values. And oh boy, are there some missing values. All right. So for each one of those variables here, as we go down the list, over here on the right, I have how many of those 454 observations had a missing value there. So usually it's just a blank string or something like that, or somebody didn't fill in a pull down. There are some which were much less popular to answer than others, okay? And, okay, great. Here's some numbers. Who cares? This is not a good visualization, right? As a working data scientist, you will probably prefer to use tools like this, which take a large tabular data set and scroll through it for you and highlight missingness, okay? So every light colored line is missing data. So this entry right here had none of those variables, that strong line all the way across, all right? We can see that some of these topics were not popular, were often not filled in. We can see that some people maybe just skipped most of it, right? We can look for correlations that might be important to us later in understanding this data set. All right. Next up is the shape of the data. So first off, once you get into statistics, you will learn that there's different shapes, different statistical distributions, all right? And that each distribution has its own set of tools. The math that's appropriate for one kind of data distribution is not appropriate for something else. And we need to know straight out the bat, is this data normal? And I don't mean that in a moral sense, okay? I just mean that is it distributed as a Gaussian, as what you already probably know as a bell-shaped curve, okay? So that is a normal or Gaussian distribution. So there are simpler distributions. So if you have dice, I don't know if you're a player of tabletop games, right? A 6-sided dice or any sided dice should theoretically have a uniform distribution. Every single number that's possible is equally likely to come up, all right? Some processes are like that, all right? So if you roll a dice 1,000,000 times, you would get pretty much the same number of entries, plus or minus almost nothing, when you do it that many times. Okay? So this is not a common thing in the natural world, though. Only really mechanical things tend to do this. Now, lots of stuff does this. This is what I said earlier, a bimodal distribution. If the numbers have twin peaks, also good show for those of you in the retro mood, right? So if we have 2 peaks in the data, that kind of implies there might actually be potentially 2 separate processes making this data, okay? So you could maybe have process 1 and process 2, and your data set encompasses both of them, okay? So again, a normal distribution is a fairly common thing in the natural world. Not everything is normal, but if you put 2 normal processes together, it will be bimodal. And when you see bimodal things, you should often think, my data might actually be capturing 2 things at once. All right, here's an example. Here is the height data you all gave me. All right, here we have something that looks like this. It's not just bimodal, it's like quadmodal. All right, what's going on here? Well, we already kind of said that we have that person over here who put in 5 for height in inches. So assumedly they're not this tall. They are probably 5 foot and they just made a mistake. I have no idea what these numbers around 200 and 500 are. People mashing the keyboard. Maybe around 200 we have tall people who thought this was centimeters. I don't know. 500 is just, yeah. All right, so almost certainly multiple things were going on with that data. You had probably most people answering actually in inches and some other kinds of weird mistakey sorts of things. All right. So if we cut away the probable mistakes and we just concentrate on a reasonable range of adult human heights, we see something that looks like it might be pretty close to a normal distribution. All right. Yeah, so here's another example of bimodality. If these are the wait times, right? So this is the amount of time, and this is when it occurs. You can see that there's kind of like a lunch rush level of time, and you have a dinner rush level of time. And you can see they're 2 different processes, And if you turn this into a histogram of time, what you would see is, so this is time again, we would see something like this. Okay, with dinner and lunch contributing like that. Oh, my stupid face is in the way. Sorry. All right, with dinner and lunch contributing like that. All right, now that you're all caught up, let me get back in the picture. All right, so the normal, the Gaussian, right? You're going to get into the math once you take a real stats course. The important things to note about it is that most values are close to the central value, right? And that the data are roughly symmetric around that central value. Okay, like we showed you with your heights. Now, sometimes a distribution does not have everything kind of equal on either side of a center, okay? Sometimes a distribution is skewed. Well, that's what happens when most values fall to one extreme within the range, okay? So a skewed left distribution has a long tail heading to the left, and a skewed right distribution has a long tail heading to the right. To keep your terminology straight, the skew is where the tail points. It's not where the bulk of the data is, it's where the tail points to the left or the right. So this is skew right data, and this is your number of siblings, all right? So most people, the single most common response is a 1, okay? But there's a fair number of people with zeros, and a reasonable number of people that have 2 siblings, and relatively few that have 4, okay? So that's just a classic skew right because the tail points to the right, okay? Most of the data is to the left. Skew left is your comfort with statistics. Actually, many of you are reasonably comfortable with statistics, which means I'm boring you to tears. And I'm sorry about that. Okay, but we have to do class to keep, to bring everybody up to speed at the same level, right? So you can also have garbage. That's what I would call this distribution, which has no apparent pattern. It could be something where random sampling is just causing a lot of randomness, but this looks relatively bad. Okay? And that's what happens with your backgrounds in programming. There's really no apparent pattern. It seems that some of you are good, some of you are middle, some of you are not good. It's all relatively even, but it's certainly not uniform. So what exactly is going on, describing the process that might have made this level of programming difference? I don't know. All right. Do not freak out. This diagram is to give you an idea of the many different shapes of statistical distributions. We've covered the normal and the uniform, and yeah, that's it, right? Some things you might be familiar with is the Bernoulli distribution, coin flipping, right? Other things I'm not even going to bother to mention, all right? You will grow to know and love all of them. So let's do it. Who wants to take a little quiz? All right? So here is your high school GPA, or at least the distribution of your high school GPA, I should say, of all of you. So which of the following best describes the shape of this plot? You can find up here the Google form link to go fill that in if for some reason you're not able to click on it. And then there are several of these that we're about to do. So I'm going to let you click through all of them, and then when you're done, you can come back and hear what I say. All right. As you may have realized, there is a tiny, tiny little bump out here. There is some data far on the right. So this is very clearly a bimodal distribution. Okay? Why is there like 89 and 90 GPAs? Well, I gather that some of you use a high school system which uses percentages instead of GPA points in the range of 0 to 4 like I grew up with, or I think California is 0 to 5, right? All right. What describes the shape of this plot? Well, you should have already clicked through and done the whole thing, so I can just tell you that to my eye, this is reasonably normal. Now there is something like a skew left going on here. It's kind of minor. So while it would show up in a measure of skewness, it's not exactly what I would call a skewed distribution. So I would call this normal. Okay, let's think about hypotheticals, like what is your expectation for something that might be uniformly distributed? Do you think it's siblings, sizes of the shoes in your closet at home, heights of a random sample of adults in the US, daily chance of winning the lottery, the distribution of speed limits in the US? Well, we already saw that number of siblings was some sort of skew right. The sizes of the shoes in your closet at home, if you live alone, they're going to be unimodal, kind of straight up and down on whatever size you have, I hope. If you live with other people, they're going to be polymodal at whatever those sizes are. So not good. The heights of random sample of adults in the US, well, we already showed you the heights one for a class of almost 400, so no. Distribution of speed limits in the US, I have no idea what that looks like. But the daily chance of winning the lottery is always probably pretty much the same, right? It's the dice roll. It's, did your numbers come up? And since numbers should come up equally likely in a mechanical lottery, this should be the answer. Okay. Which of the following would you expect to be my bimodal? Well, kind of already gave it away, right? So actually, you can make an argument for two of these, right? So if you live with one other person and they have different size feet, okay, the heights of a random sample of adults in the US is the likely answer. So we have, generally speaking, two separate groups. Actually, I should do it this way. So, man, I'm getting bad at drawing this. All right. So generally, males have a slightly higher height than females. It's true on average, but the distributions overlap quite a lot. So that produces overall a bimodal thing. Okay. Now, one of my favorite topics in statistics. When do you say, screw it, this is not good data, and throw it out? Right? There are things, outliers. So it's kind of like when you have a bimodal distribution where you have multiple things that are showing up in your data, all right? Well, when you only have really one process and then two random things that are not from that process, then you have an outlier, all right? So it's not quite ready to be a multimodal distribution. You only have a couple out there on the edges, all right? So when you see an outlier, some sort of little bump far, far away from where most of the rest of your data is, it looks funny. It might be something that you want to exclude from your analysis for one reason or another. So, right, this was supposed to be data for 1,000 people that were collected in adulthood, 18 to 65, all right? But somebody screwed up and 2 extra records were thrown in, a 1-year-old and a 95-year-old, okay? Because your study is looking at the health of adults, really old and really young are not appropriate to include. So when you see that, you may want to get rid of these outliers so they don't affect your study. All right. Outliers happen, of course, due to error, poor sampling. It can also just be mechanical or technical that something happens. The machine broke that day and nobody realized and you still collected data. You could have something where a sudden cold snap causes some sort of measurement to be different than you wouldn't expect, okay? And of course, people just throw in 5 when what they thought was feet and is actually inches, all right? So, if you have a strong reason to know that these are some sort of inconsistent, doesn't come from what I want kind of data, all right? You have to have a really good reason, not a just, it will make my life easier, okay? Not just, this is messy. It shouldn't be like this. No, that's not a good reason. But rather, you've traced the source of the error, right? You found the data entry error, right? Or we have a strong reason to think that that person is not 5 inches, but rather they meant 5 feet, okay? Right? We have to have some good reason to exclude the data. So you only want to remove observations when you really have a good reason, backed up by evidence and strong logic. And if you present it to 5 other people, they all agree, yeah, that's probably a good reason to exclude data. Okay? If they argue with you, don't exclude the data. Right? And if you do exclude the data, tell everybody. Make sure you report when you make the analysis that you excluded this data and this is why, okay? If you don't do that, you're doing it wrong. You're not doing a transparent, reproducible analysis, right? Because if you just exclude these and you never tell anybody about that, then somebody else does the study, they're going to have the same problem and they're going to get a different result than you. Okay? All right, central tendency. So any of these distributions, it doesn't matter if it's normal or skewed or whatever, they all have some sort of middle point. Okay, and we're going to describe several different ways to measure that central tendency. Okay, you're probably familiar with mean or average. Basically everybody who comes through high school knows what that means. But you may not be less familiar with median and mode. Let's get you up to speed. All right? So here is a set of numbers. And it just so happens that the mean value is 3.5, right? We just sum up all the values, and then we divide by the number of observations. So this is a little different when we look at my face. Hey, I want that. There we go. Back here to median. So the median, just mathematically, is the sum of all the values. Okay? Normalized by the number of values. So there's, add it all up and go for it, right? Now, the median, whoops, I drew that on median, didn't I? whatever. All right. So that's where I meant to draw this. And the median is simply when you order all the values. Oh, stop it. When you order all the values, get away. All right, you can tell it's getting late at night. All right, you order up all the values 1 to 6, and you find the middle one. Well, there's no middle one in an even number of things, so we just find 3.5. All right. Now, if we add in an extra 3, now the median is 3. Okay, because it's the one in the middle of the running order 1, 2, 3, 3, 4, 5, 6. Okay, so for the original formulation of this, the median and the mean are identical. They're both 3.5. But in this formulation on the bottom there, right, the median is 3, but the mean is 3.42. So over there. All right. So here's an example from the last time COGS 9 was run. Okay, the last time they didn't get that person with a 5 down here. Okay, so since they didn't have that, but they did have some people entering in random BS up at 1200. So they got a very interesting distribution. One where the median is 68 inches, which is a totally reasonable human height. But the mean is 376 inches, 376,588 inches. Wow. That wasn't 12,000, that's 12 billion. No, 12 million is 6, 7, and that's 8. Yeah, okay, 120 million. So one entry of 120 million, one single person, right, has skewed the mean. You may have heard the joke before, right? Means are not robust, okay? One single weird outlier, remember outliers? One single weird outlier changes the mean dramatically, okay? And if you think that you might have weird examples in your data, sometimes the mean is not a good thing to use to measure. All right? The old joke is there's a bar, Bill Gates walks in, suddenly the average amount of wealth is over $1 million in the room. Okay? All right. Okay, so I didn't want to have that there. I don't know why that slide was there. I wanted to use the old one because they had this problem where the median is 68 and the mean is 376,000. Which one do you think is actually a better measure of central tendency? Well, that was what I was just saying, is that when there's weird outliers, there's a good reason to use median. It's more robust to weird outliers. It tends to capture the average better. Oh, now I know why I had that there. Right. So let's look at your guys' height. All right. So the mean value here for your data is 63 inches. Okay. That includes our 5-inch person in that mean, and our almost 200-ish, and our 500-ish person. Okay? Actually, there's several here at 200. Okay? So the mean value is, whatever, something like over here-ish. Now, this is the median. The median is also called the 50th percentile. Now this is good to know, right? If we order people 0 to 100, where 100% or 100th percentile is the very top of all humanity and 0 is the very bottom of all humanity, then the middle, the median, is the 50th percentile. Okay? And that's sometimes written like that, or like that. Okay? We have to press on. I'm realizing that I'm being quite slow with all these. So, the mean and the median are used to summarize the central tendency of things. Mode is helpful for describing a categorical central tendency, all right? We've been talking about real numbers completely so far. So let's talk about categories, right? What is the most commonly observed hair color? All right? Well, black, right, in this data. All right, variability. Finally, our last chunk. So the central tendency of the data only tells you part of the story, right? So we could have two normal distributions, one of which is rather peaky and tight, and one of which is rather flat and loose. They both have an identical central tendency, but they have very different spread. And that's what variability is. Okay? It tells you how spread out those variables are. So if we do the percentile trick, right? We go 0 to 100. We have, in the middle, we have 50. We can get some understanding of how spread out things are by checking the 25 and the 75. Okay? So this in here is half of the data. By definition, the middle half of the data, 20 to 75. All right? So for something big and spread out like that, the middle half of the data will be this wide. For something that's peaky and narrow, the middle half of the data will be that wide. So you can see that we can have very good ideas of how spread out the data is by using the 75th and 25th percentile. This also has an advantage, this method, because it's generic according to the distribution. This works for things that are normal and it works for things that are not normally distributed. Okay? Oh look, I didn't have to draw that stuff. So, so another thing to point out is that, so I just showed you that, but this is a box plot. We've shown box plots before. All right, this value is the 25th percentile, and this value is the 75th percentile. Okay, and this strong line in the middle, that's the median. Right? That is the definition of what a box plot is. And this is exciting, right? The difference between the first quarter and the last quarter, in between that, is called the interquartile range, the IQR. Okay? Such a great bit of statistics jargon. Okay. So the last thing that you can do for variability is you can measure variance. Variance is a quantity which is predicated on the average. Okay? So the amount of difference for each point, how far away it is from the average, sum over all the points squared, and normalize by the sample size. All right? It's the average difference of each individual dot compared to the mean. All right? So to give you an example, here we're going to calculate, for our example, we have to calculate the sample mean, and we know that's 3.5. All right? So we plug that in there. Now we have all these numbers, right? So we have to take 1 and put it in. 1 minus 3.5 squared plus 2 minus 3.5 squared plus 3 minus 3.5 squared, and so on, until we add that all up and we get 17.5. Then finally we normalize by n minus 1. Okay, and the result of that is a calculation that says that the variance is 3.5. So we have a central tendency of 3.5 and a spread of 3.5, which is obviously exactly true in this case. All right. What happens if we jack around with it a little bit, right? We just calculated 3.5 for this, but if we change 5 and 6 into 9 and 15, and we spread things out, we get 24.7. So we've spread the distribution out greatly. All right, and finally, the standard deviation is a term you will hear. All it is the square root of the variance. So we just calculate everything we did before, and we get that standard deviation, this variance is 3.5, square root it, that's 1.87. So these are all different measures that are used at different times to give you an idea of the spread of the data. All right? So here's why central tendency doesn't tell the whole story, right? Just like I kind of predicated before. Same central tendency, and the tails are dramatically different, right? Here's 20 and 30 point. So like almost 16% of the distribution is underneath that side, that tail. And here just about 2% is. Okay? So know your data. That is all I had for you. I've gone almost a full 10 minutes over. I apologize for that. I hope that you all had a really great midterm, and I promise that we're going to get you your grades back just as soon as we can. All right? In the meantime, enjoy, and I will talk to you next time. Magic is asleep right over there, and he would say goodbye otherwise.